Hello. You're all right? Going to do a fun thing today. Can do. All right. This. So you remember this? I forgot my pointer again. Rookie mistakes. We were supposed to be making chess sets, small sets and large sets, and we were trying to maximize the profit. You still remember that? Must do. So I've been talking about this many times. So we've got this problem where x1 is the number of small sets to produce, is the number of large sets to produce, and there are three constraints related to some machines or something like that. And the objective function gives us the profit that we can achieve by producing x1 of the small sets and x2 of the large sets. And now we know how to solve this. Of course, we remember how to solve this, but let's imagine that somebody comes and says, is it possible to have profit £1,300 or more? So of course we know how to do what to do, right? If we solve the problem and we find the maximum profit, we'll compare the maximum profit with 1,300, and we're going to say, well, yes, or well, no. But there is an easier way to establish whether we can have this much profit or not. And the way I'm thinking about is, look at the third constraint here. If we multiply this constraint by 40, why 40? Well, because I tell you so. We get that 20x1 plus 20x2 is less than or equal to 1,240. Do you agree? Yeah? Okay, now, this, however, is certainly not less than 15x1 plus 20x2, right? Because x1 is non-negative, so if instead of taking 20x1, we take 15x1, we're not going to make the expression larger. What did I say? Probably said it the wrong way around. So, but if instead of 15x1, so 15 times something positive, we take 20 times something positive, we can only increase the value. Okay? So we have this inequality, and this is the objective function. Okay, so what we can see is that if we take x1 and x2 that satisfy the third inequality, and there's no way we could achieve the value of z 1,300, because it will certainly not be more than 1,240. Okay, so any x1, x2 that satisfy the constraint. 3 do not. Give us this, so that proves that profit of 1,300 or more is not possible. Make sense? Great. Now we can actually do a little bit better than this. For example, if we decided to take 2 times the second constraint and add to it but one of the purposes of this lecture is actually to get somehow to the point where we will know how to come up with these numbers. Okay, so I'm inventing them because I know. So bear with me for a minute. Now, trust me that these are good values to take. And what we're going to have is, so on the right-hand side, we have, well, 2 times 200 plus 27 times 31, which is, oh, I don't know what that is. I got, well, 37. If you're especially eager, you can verify that that's the right number. On the left-hand side, we get, so what's the coefficient of x2? Well, 8 plus 13.5, so that's 21.5, so 43 halves. And what's the coefficient of x1? Well, here we get 2, and here we get 13.5, so it's 15.5. So it's 31 over 2, x1. And that, again, because this number is more than 15, and this number is more than 20, we get 15x1 plus 20x2, which is the objective. So, in no feasible solution, okay, I'll put it this way. In a feasible solution, Z, the objective is no more than 1,237. Again, it's not a huge improvement on the 1,240 that we had before, but it shows that perhaps we can do even better. Do you think we can do better than that? So the question asks us, what's the best thing we can get from this method? Well, what is the method? The method is we multiply each of the constraints, or some of the constraints, by some positive numbers or non-negative numbers, add them all together, and what we get here, we get that this coefficient must be at least 15, and this coefficient must be at least 20. Okay, and if we get that, then we get the right-hand side it's going to tell us that the objective cannot be larger than that. Okay? So again, if I move on, this. What are we doing? We are timesing this inequality by a number. I'll call it y1. We're timesing this inequality by a number, I'll call it y2. And this inequality by a number, and I'll call it y3. Okay? And we do that and add these three constraints together, what we're going to get is, well, the coefficient of x1 is going to be 3y1 plus y2 plus 1/2 of y3. And that's what's going to sit at x1. Okay. For x2, it's going to be 2y1 plus 4y2 plus 1/2 y3. Okay. And the right-hand side is going to be 160 y1, 200 y2 plus 31 y3. Okay. So this is the method. Now, for this to work, we need, as I said, we need this to be at least 15, this be at least 20, okay? And we want the best one possible. We want this to be as small as possible. Okay, the smaller it gets, the better, because the smaller it gets, the lower the bound gets that we can't exceed. And we want the bound that we can't exceed to be as low as possible. Okay? So these are the things that we want. And we also want one crucial thing, and that is we want all these numbers to be not be negative, because if they were negative, it would break. Because if they were negative and we would times this equation, this inequality, not equation, that's the point, this inequality by something negative, that will flip the sign, the inequality sign, the wrong way. So we want these y1, y2, y3 not to be negative. Okay? And so the best bound we can get using this method, we get by solving the following problem. We want to minimize, because we want to make this as small as possible. So it's 160 times y1 plus 200 times y2 plus 31 times y3. And we need to preserve the constraint that 3y1 plus y2 plus 1/2 y3 should be greater than or equal to 15. And 2y1 plus 4 y2 y3 should be greater than or equal to 20, and all these y's non-negative. Quite fancy. Do you like it? It's very exciting, isn't it? So we tried to solve a linear programming problem with x's and something. And instead of solving it, we said, oh, what's the best upper bound we can get by combining the constraints? And the best bound we can get is given by solving a different linear programming problem. This is a linear programming problem of its own. Yeah? That's very fancy. Have you solved it yet? In fact, you don't have to solve it because the next page of the handout gives you the solution. And here you can see that for some reason the objective of this optimal solution, which is the best upper bound we can get, is coincidentally, apparently, the same as the optimal solution of the problem that we started with, isn't it? So the optimal solution to the thing which is called the dual, the new E, has the same objective value as the old one. So what I call new is actually called the dual linear program to the old one. Definition. Okay. The question is it always, is this a specially crafted LP where the dual gives you the same answer as the old one, the primal? Or is this the case no matter what we start with? That is a big question. Now, okay, before we answer that question, I'll make a remark. So the remark is, when you look at these numbers, 5/3 and 80/3, that's how I got my 2 and 27, just rounded 5/3 up to 2 and 80/3 up to 27. And I was hoping that that would give me a sort of a nice, good, decent, feasible solution to the dual, so a good bump. Okay. Any questions about this or any issues with it? You can kind of see the pattern emerging. When you get one linear program and you want to get the dual one, what you do is, well, as we did, you need for every, we did here, that one. See there, you need one decision variable for each of the old constraints, And then for each of the old decision variables, you'll get one constraint. Okay, so the 15 here is the 15 from this constraint, and the 20 here is the 20 from this constraint. And then these 160, 231 get into the objective, and the coefficients around here, so 3 and 2, 3 and 2, 1 and 4, 1 and 4, half and half, half and half. Okay, so kind of got transposed to the matrix. So that's the next thing. Look at that. That's what a linear programming problem is, right? So that's what we usually did. So you have some numbers, A's, B's, and C's, and some decision variables. Those are the X's. You've got plenty of decision variables, and you've got plenty of constraints, and you put them into a system like this. But for various things, it's more useful to write the C's, X's, and B's as vectors. So you'll have one vector, which is C, which goes C1, C2, and Cn are the entries in that vector, like this. And the X's are a vector of X1, X2, Xn. And then the objective is just C times X. So when you multiply a row vector like this with a column vector like that, you know from your linear algebra that what you're going to get is C1x1 plus C2x2 plus dot, dot, dot plus Cnxn. Okay? And similarly, you can write, I can use the mouse. You can write this whole thing, okay, as some matrix A, where all the little a's are entries in that matrix, and you multiply it by the vector of x's like this. Okay. It's a little bit perhaps fuzzy because so C times X, that's just a number. It's the product of two vertices, like the inner product, or what you call it, scalar product of two vectors. That should be familiar. However, this A times X, you take a matrix that has n columns and m rows and multiply it with an n vector, you're going to get a vector that has m entries. Okay, m rows. So this less than or equal to b means that every so what are they? Okay, let's go back to this. So this is 1 by 1 because C is 1 by n. And this is n by 1. So if you multiply C times X, you get 1 by 1. So that's just a number. So you know what to do with a number when you're minimizing it. But A is n by n. There's n rows, n columns. And B is n rows, 1 column. So when you do A times X, what you're going to get is n by 1. And this is also n by 1. So what you're actually comparing is less than or equal to here means entry by entry. Okay, so each number, first number in the first vector has to be less than or equal to the first number in the second vector. And the second number in the first is less than or equal to the second number, and the third is less than or equal to the okay? Like this, you get exactly the equations of the linear programming problem. Is this too tough now? It's just notation. But the problem is, okay, I'll make a side remark because I'm getting tired. So the problem is, that is not like a mathematically deep idea there, but it's a notational thing. Right? So you just change the way you write things into like a different language almost, and sometimes it takes time to get used to that new language. But there's not much I can do for you. You just have to go through it again and again and again and see many examples like that, and then you do it. Because when you're learning maths, nobody can do it for you. When you're learning maths, you just have to do it inside your head. I think I told you this analogy, like between maths and music. Adrian's smiling. Yeah, so when you know nothing about music and you see a sheet of music, it makes no sense to you. Right? So funny symbols and so on and so on. And then a musician comes and they read the music from the sheet, and to them it makes perfect sense. Okay, so they can take this sheet of music and they can play an instrument, or the orchestra can play it. It's more complex, or someone can sing it, and you hear the music. But if you're not used to the notation, how it's written, and you have no idea what's going on there. Is that right? It's similar in maths. In maths, it's written in a way that many people won't understand because they're just not used to writing things in that way. But if a mathematician comes, they can play the music in their head and it suddenly makes sense. Now, there's a bit of a difference there because whereas the musician can quite easily play the music and you, without being able to read everything, can see that it's beautiful music. In maths, it doesn't quite work that way. You really have to process it yourself. There's no way. I mean, I can help you. Anybody can help you. But I can't just, I can't just make it happen. It has to happen inside your brain. That's the main difference. Put up the arm and talk too much. What's next? Oh. So, going back to this. I've just rewritten what is on here. So that was our original linear program. Okay. And I said you should take one decision variable for each of the constraints and multiply the constraints. And as you can see, what was it again? I'll go back here. As you can see here, what was the right-hand side? Okay. Now we call this B. That became the objective. And what was the objective? That was the CX. Okay, the C's, they started being here. It's actually C transposed because I'm making a row vector into a column vector. And here I'm making a column vector into a row vector, so I'll have to transpose it. And what happened with, so these are the A's, right? So this is A times X. And if you just look at the numbers, 3, 2, 1, 4, half, half, they form the matrix A in our new matrix notation. Okay? And what happens here is that the matrix is 3, 1, 1 half, 2, 4, 1 half. So that's, I'm sure you know from linear algebra as the transposed matrix. Matrix transposed. You know that? Transpose? Yeah? Excellent. So this is exactly what happened. Okay? That's what I've got here. The coefficients in the objective come from the right-hand side. The right-hand sides here come from the original, oh, I can even highlight like this. From the original objective, this matrix of coefficients in the inequalities is transposed. Non-negativity is still non-negativity. Maximize, come on, didn't highlight anymore. Maximize is changed into minimize, and And in the maximize, we had less than or equal to, whereas in the minimize, we have greater than or equal to. And that's how it works. Do you agree? That's how it works. And now we've got the theorem. No, I'll put this back here and put the theorem. Okay, so what does the theorem say? P, that's our old. P is the new. Actually, that is very interesting, is that if you start with the new and do this process on it, you get the old. So there are only two of them. It doesn't go on and on and on. You can't keep creating new linear problems because if you do the same trick on the one you got as the dual, you get the primal back that you started with. So in other words, linear programs come in couples. And the coupling works like this. So if one of them is unbounded, that means that the other one is infeasible. Well, that's kind of easy to see because any feasible solution to the dual, yeah, we designed it to give some upper bound on the objective. If there's no upper bound on the objective of the primal, then there can't be any feasible solution of the dual. Okay? And it works the other way as well. This is just a symmetric statement. And that's what interesting is, if one of them is feasible and bounded, then so is the other one. And they both have a finite optimal solution, and their optimal solutions always have the same objective value. Okay? So it wasn't a coincidence, it actually happens every time when you start with a linear program and you do its dual. It doesn't matter which one you solve, because each of them will give you the same optimal objective. Okay, that's quite very useful in many situations, which we won't really go through. The proof is next year if you if you choose the operational research unit for your next year, we'll do the proof and also some more applications because it really appears in many different situations and it's very useful. So there are many things why this is good. One of them is that it's basically at the heart of a theoretical explanation why we can solve linear programs very quickly. Because when people study lots of other optimization problems, there's always some sort of duality like this. So you can always try and you have an optimization problem which is not necessarily linear. You can always try and produce some kind of dual problem. But in many situations, there is what's called a duality gap. So the two problems won't have the same optimal objective value, and they're notoriously hard to solve, and so on and so on. But linear programming is beautiful because of duality. Duality is one of the reasons that makes it really nice and useful. And many other things, Any questions about this duality? Okay, so I think it's time to take a 10-minute break, and after the break, we're going to have another look at the maximum flow problem that we started last week and see what duality does to it. And that will finish the whole linear programming thing, so you can check. And then next week we'll start game theory.